comes to uncovering the ultimate truths about reality, we can only reap what we sow. Without a cutting-edge particle collider like the Large Hadron Collider at CERN, we would never have discovered the Higgs boson. Without the incredible sensitivities achieved by gravitational wave detectors such as LIGO and Virgo, we would never have directly detected gravitational waves. And without a revolutionary space telescope like JWST, the overwhelming majority of the universe, which has since been revealed to us in exquisite detail, would have remained obscure. By the 2030s and beyond, with even more capable space observatories available, the exoplanet community aspires to routinely detect, identify, and study habitable worlds, and ultimately hunt for telltale signs of life. LUVOIR, which is short for Large Ultraviolet Optical Infrared Surveyor, continues NASA's tradition of observing a wide range of electromagnetic wavelengths in order to push the limits of our understanding within and beyond the solar system. For the first time in history, we are designing a space telescope with the main intention of detecting and characterizing habitable worlds in unprecedented detail. LUVOIR. If you've ever dreamed about knowing the answers to the biggest questions of all, this is the one telescope that we absolutely must build. You want to know why? Then stay tuned. Despite showcasing a cutting-edge technology, there is a limiting factor to JWST's equipment. The reason it can't observe at wavelengths longer than about 30 microns, or about 15 times as long as the limit of human vision, is because it gets heated by the sun. Just as infrared cameras revealed heat sources, the inside of JWST is too warm to observe at mid and far infrared wavelengths. JWST's other major limitation is its narrow field of view. Even with the most advanced camera ever installed on it, the Advanced Camera for Survey's Wide Field Camera 3, it can only achieve resolutions of approximately 8 megapixels. When you take into account the mirror size and focal length of JWST, optical properties that are second nature to astronomers, it can resolve objects down to angular resolutions of just 0.04 arcseconds, or just 1/90,000th of a degree. If you put the JWST Space Telescope in New York, it could resolve two separate fireflies in Tokyo if they were separated by merely 3 meters. Yet even at the full extent of its capabilities, even with the equivalent of a month of continuous observing, JWST can still only see an estimated 40% of the galaxies that are out there. Most of them are some combination of too small, too faint, too distant, and too obscured by neutral atoms to be seen by JWST. Moreover, even the majority of galaxies that are revealed are barely more than a few points, as JWST is too small in size with too little resolving power to reveal additional details. In many ways, JWST represents the greatest astronomical endeavor ever undertaken by our civilization, but it's also fundamentally limited. But even with these advances, there are still questions that we want answers to. Big, important, even existential questions that will go unanswered. Even with Webb and Roman, most of the galaxies in the universe, even in a tiny, narrow region of space, will remain elusive. Most of the galaxies that we do see will still, unfortunately, simply be a few pixels across, with a barely discernible structure. And perhaps most importantly, they won't have the ultimate capabilities of a space-based observatory, the ability to directly image Earth-sized planets around sun-like stars, and to identify which ones might not only have signatures for life, but might actually be inhabited. But there is one telescope that's been designed that could accomplish all of these, and it's one of the 4 finalists to determine what NASA's plan for astrophysics flagship missions will be for the 2030s, LUVOIR. It's the Large Ultraviolet Optical and Infrared Telescope. Basically, you should imagine a version of the largest functional ground-based telescopes we have operating today, telescopes like the ones at Keck Observatory of the Grand Telescope, Canarias, equipping it with the greatest instruments that modern technology can offer and launching it into space. That's LUVOIR. In terms of what LUVOIR will bring us, it's hard to overstate just how powerful an observatory like this would be. Sure, its technical specifications are impressive, but what's really important is how it will help answer some of the biggest questions we have about the universe today. So are there any inhabited planets nearby? Note the use of that word inhabited. We're not talking about looking for potentially habitable worlds, nor worlds with bio-hints or biosignatures, nor worlds that might be capable of someday being home to humans. We're talking about the big one, finding out if the nearest Earth-like planets actually have life on them. And we're not talking about one or two nearby planets, but dozens and potentially even hundreds. We'll not only be able to directly image these worlds with LUVOIR, we'll be able to determine what fraction of them are covered in continents versus oceans. What are the properties and coverage of clouds on those planets? Whether their land masses are green and brown and ice over with the changing seasons. What their atmospheres are made out of. Whether there's any evidence of oxygen, nitrogen, methane, carbon dioxide, or even complex molecules. And what it all means for the existence of life on those worlds. As LUVOIR scientist Jason Tumlinson said, it could explore dozens of Earth-like planets and assay their atmospheres. Detecting an exoplanet showing signs of life would be a discovery on the level of Newton, Einstein, Darwin, quantum mechanics, JWST's expansion, you name it. LUVOIR is the first telescope designed from the beginning for this revolutionary purpose. The ability to finally reveal almost all of the objects that JWST and Roman will overlook. With LUVOIR's size, optical capabilities, and novel instrumentation, it will surpass all previous limits in terms of what it can discover. The jump from JWST at the absolute limit of the faintest objects in the extreme deep field to LUVOIR will reveal objects a whopping 40 times fainter than we can presently see. That's the same leap from large ground-based telescopes to JWST, or from a 30-second exposure with a 2-meter telescope to an all-night exposure with the largest telescopes presently in the world. This will reveal smaller, fainter galaxies in greater numbers and at greater distances than any other observatory ever. It will discover greater numbers of smaller, fainter, and more distant objects in our solar system than every other observatory ever built combined. It will take images of the outer planets that are just as good as the images taken by Voyager 1 and 2 when they physically journeyed there, and it can do so anytime we choose. It will find, measure, and characterize individual stars fainter and farther away than ever before, including an unprecedented number of galaxies over 1 billion light-years away. Basically, if you're looking for objects that are faint, far away, small, or otherwise difficult to characterize, LUVOIR will not only find them if you know where to look, but it can tell you far more about its details than any other tool. So what does any galaxy in the universe in detail look like? Imagine being able to point your telescope at any galaxy in the universe, an object typically around 100,000 light-years across, and no matter how far away it is, still being able to see features in it as small as 300 light-years across. For a galaxy the size of the Milky Way, no matter how distant it is from us, LUVOIR would show it as at least 400 pixels across, containing over 120,000 pixels of useful, luminous information in every frame. The same galaxy, if it were imaged with JWST in the same amount of time, would contain only 50% of the information contained in a LUVOIR image, with vastly inferior resolution and light-gathering power. We could learn how each galaxy we measure rotates, which regions in every galaxy are actively forming stars, what the distribution of gas and dust is in every galaxy, what satellites and dwarf galaxies are doing out to billions of light-years, and so much more. From objects within our solar system to exoplanets, stars, galaxies, and the largest cosmic structures of all, LUVOIR would answer the biggest questions we have about our universe. All we have to do is make our dreams of knowing what's out there in the universe come true, is choose to build it. Our ultimate hope is that we won't just build LUVOIR, the best of the present options, but an array of observatories one after the other that will all cover different wavelengths and work to complement one another. Origins, a far-infrared telescope, is ideal for measuring details about planets and stars still in the process of forming. Lynx, an X-ray telescope, could reveal details about black holes, neutron stars, and colliding galaxies that nothing else can see. Even HAB-X, an exoplanet-optimized mission inferior to LUVOIR in every way, could launch on a much shorter timescale, making it an attractive option. Astronomers around the world are hoping that with LUVOIR, the most powerful and ambitious space-based observatory ever proposed, we can find definitive answers to the biggest questions of all. It takes a big effort and a substantial investment, considering that the reward is learning that there's life on that planet orbiting another star right over there. It's clear that LUVOIR is the one telescope we must all join together to build. So what are your thoughts on the LUVOIR telescope? What do you think NASA is going to select as its next big space telescope that will shape scientists' research in the 2040s? Let us know in the comments below. Thanks for watching. Be sure to like and subscribe to the channel for more interesting content like this.